Here I have a little more advanced version of a partial fraction decomposition. This time we have a cubic in the denominator, all right? And this is specifically a case where the cubic is going to factor down into linear terms. In other words, each value of the factorization is going to have an x term only. We're not going to have like a quadratic that doesn't factor or anything like that. The process is a little different if that happens. So anyway, the big idea here, if you remember, is you need to factor that denominator however you think you can factor that denominator, all right? So for example, you might notice that this could be factored by grouping. This is x cubed plus 2x squared minus x minus 2. I see a lot of x's and 2's there, and I realize, hey, if I group these together and I divide out a GCF of x squared, I get an x plus 2 inside parentheses. If I divide a negative 1 out of this, I get an x plus 2 as well. Now I have this term minus this term. Notice both of those have a factor of x plus 2. I can factor out the x plus 2. I get an x squared minus 1 left. That's a difference of squares. And so my factorization is the quantity x plus 2 times quantity x plus 1 times quantity x minus 1. Okay, that's going to be the factorization. All right? Now, there are other approaches here. For example, if you wanted to try to break this down using synthetic division, for example. We know that any factors are going to be in the form plus or minus 2 over 1, okay? And so, for example, if I put negative 2 in here, negative 2 cubed is negative 8. Negative 2 squared times 2 is positive 8. Negative 2 is positive 2, and then minus 2 equals 0. So by the remainder theorem, we can see the remainder would be 0 if we sub in negative 2. Of course, by the factor theorem, that means that we can divide out that factor. So if negative 2 is a 0, that means that x plus 2 would be something that could be factored out of that expression, and then we could go to synthetic division. So you put a little negative 2 in your box, you've got a 1, a 2, a negative 1, and a negative 2. And anyway, you can go through the song and dance here, and you're going to end up with x squared minus 1 as your remaining part. That is a difference of squares, and so we get a quantity x plus 1 times quantity x minus 1. So it doesn't matter how you do it. Most of the time you're going to have to use this approach. It just happened that the example that I had could also be factored by grouping, which happens on occasion. All right, so here's the key. That denominator factors as x plus 2 times x plus 1 times x minus 1, all right? And because we have different terms here, if they're repeated, the game changes a little bit, but they're all linear. They all just have an x variable. We should just be able to break this up very much like the previous examples. I can do a over x plus 2 plus b over x plus 1 plus c over x minus 1, okay? And we should be able to get everything to work out real nicely. All right, now, you know what, let me space this out just a little bit. Hopefully that's all on the screen. Yes, it is. All right. Okay, so again, you need a common denominator. Okay, the common denominator is going to be the product of all three denominators. So you could get a common denominator. Remember that you can actually just knock out the denominator. You can multiply everything by the common denominator. So multiply this by the quantity x plus 2 times quantity x plus 1 times quantity x minus 1. Okay, and that's going to knock out the entire denominator. Okay, if I multiply this side by that common denominator, I have to multiply the terms in this side by that common denominator. So I would have an x plus 2 and an x plus 1, and I would have an x minus 1. Okay, notice the x plus 2's are going to cancel. It's the whole reason for multiplying by the common denominator. And then I'm going to multiply this term by x plus 2 times x plus 1 times x minus 1, and that's going to knock out that x plus 1 denominator. And then finally, I'm going to multiply this by x plus 2 times x plus 1 times x minus 1, and it's going to knock out that x minus 1 denominator. Okay, and so we can simplify this down. We're going to have no denominators, which is fantastic. We now have 5x plus 7 is equal to, that's going to be x squared minus 1, and the whole thing is being multiplied by a. So that's ax squared minus a, all right? X plus 2 times x minus 1 is going to be x squared plus x minus 2. That whole thing is being multiplied by b. So that's going to give me a bx squared, it's going to give me a bx, that's going to give me a minus 2b. Okay? This multiplies to be x squared plus 3x plus 2. Whole thing's being multiplied by c. So that is cx squared plus 3cx plus 2c, if we want to put all of that together. Okay? So it's big, it's long, it's ugly, it's complicated. However, really, what we have here is 0x squared plus 5x plus 7. In other words, I want to match up all my x squared terms, I want to match up all my x terms, and I want to match up all my constant terms. Okay? So let's take a look at this. We don't have any x squared terms over here. So I have an x squared term here, I have an x squared term here, and that should be, is that a bx squared? That should be a cx squared there, sorry. Okay, so that tells me that a plus b plus c is supposed to add up to equal 0, okay? Now I need to look at my x terms, okay? My x terms, of course, they're supposed to add up to 5x, okay? So I have a bx and I have a 3cx, okay? And so, of course, what that's supposed to end up being, that's bx, it's b plus 3c multiplied by x squared, if I group those together. So b plus 3c, sorry, it's supposed to be multiplied by x. Wait a second. Sorry, b plus 3c times x, okay? So b plus 3c is supposed to be equal to 5, okay? So b plus 3c is supposed to be equal to 5. We have that, okay? And now I can look at my constant terms, okay? My constant terms need to add up to 7. So I have a constant term here, I have a constant term there, and I have a constant term there, okay? So negative a minus 2b plus 2c is supposed to add up to equal a constant term of 7, okay? All right, now I should be able to solve this system. Can get a little bit messy at this point. I think I'm going to try to knock out the, let's see, which term do I want to knock out first here? Should be able to knock out, well actually if I add these two equations together, I can knock out the a term. So if I add these two together, we're going to get, oh yeah, that'll be great, because I have an equation that already has b's and c's, so if I knock out the a's here, I can match it up with that. So I'm going to take that equation, b plus 3c equals 5. And of course, you can solve this system using matrices or any approach you want. I'm going to do it by hand though. If I add these two equations, the a's are going to cancel. I'll get a negative b, and I'll get a 3c, and then I'll get a 0 plus 7 is equal to 7. If we add these, the b's are going to cancel. We get 6c is equal to 12. Looks like c is going to be equal to 2, okay? And now that I know that c is equal to 2, I can substitute that back into this equation. B plus 6 is 5, so b is going to be negative 1. Okay, and finally, a plus b plus c is supposed to be 0, so that's negative 1, that's 2, and let's see, these two things add up to 1, so if that's negative 1, I would get a sum of 0. Okay, so a is 1, oops, sorry, a is negative 1, b is negative 1, and c is going to be 2. Okay, and again, board got pretty messy here. Remember what my original setup was. It was a over x plus 2. Okay, so a is negative 1, so it's going to be negative 1 over x plus 2, plus b over x plus 1. Okay, b is negative 1 there, so negative 1 over x plus 1. And then finally, plus c over x minus 1. C here is 2, and so we'll get 2 over x minus 1. And that is the equivalent of the original statement.